This is the final submission video for ISEC Space Elevator Challenge 2025. Hi everyone, I'm Makinari Ogawa from Japan. I'm going to talk about our mission, Space Habitat with Improved Hyperion Construction applying Space Elevator at L5 Point. First, let me introduce our team. On the left side is me, and the right side is my teammate Yoshinawa Kobayashi, and we are both from the Department of Mechanical Aerospace Engineering, Undergraduate School of Engineering. Our advisor, Kuzuno, he is from the Department of Aerospace Engineering and the Graduate School of Tohoku University, and currently he's doing researches on numerical simulation of flexible space structures, including space elevators. He's also the second place winner on ISEC Space Elevator Challenge 2023. To start with, there are three types of current space settlements: Dumbo settlement, Hyperion, and O'Neill cylinder colony. In order to build a space settlement in space, there are three requirements we have to accomplish. Firstly, we should have a 1G gravitational force. Secondly, we should have an environment that exhibits a 24-hour day-night cycle. Lastly, an ecosystem akin to Earth is required. However, Dumbo settlement is too small for its scale, so it can't suit multiple requirements of the habitats. Also, O'Neill cylinder colony is so large, so it is not practical to build in current technology. On contrast, Hyperion as a non-spherical object is more easy to build, and its circular structure and practical materials and living space arrangements will enable us to accomplish this mission. Therefore, we decided to build a Hyperion construction at L5 Point. In this mission, we will basically use space elevator as the means of transportation because space elevator is good for its low cost of transportation, large capability, reusability, and smaller stress for payloads. The objectives of this research is to investigate the feasibility and efficiency of space elevator for space habitat construction at L5 Point. According to the previous studies by NSS and Doris, we can find that there are no information about transportation means and specific construction methods. However, there are no detailed information about L5 Point. Therefore, in this research, we improved the Hyperion structure and suggested its construction method, and also analyzed the characteristics of L5 Point and suggested utilizing space elevator for the construction of Hyperion. Our basic concept is like this. First, we transport goods from Earth to a controllable height via space elevator, and we slingshot to Moon at L5 Point. Then, we use lunar L5 space elevator to transport goods from Moon to L5 Point, and lastly, build a space settlement at L5 Point. So, what is Lagrange point? Lagrange points are 5 distinct points which gravitational equilibrium can be maintained in Earth-Moon system. As you can see in this figure, L1, L2 is quite near to the Moon, and L3 is on the opposite side of the Earth from the Moon. However, L4 and L5 are known as stable symmetry point. So in this research, we decided to examine the feasibility of L5 point.
To investigate the stability of L5, we employed an eigenvalue analysis of the equations of motion. The force acting on a particle in the system can be expressed by the equation in the slide. We then express the equations of motion in matrix form. By examining the eigenvalues of this matrix, we can analyze the characteristics of the motion. The eigenvalues are as shown in the table. Since L1, L2, and L3 have positive real parts, their orbits diverge. However, for L5, all real parts are zero, so the orbit does not diverge and it can maintain stability. Additionally, the simulation results of particle around each Lagrange point are shown in the image. As can be seen from the maximum value of the vertical axis, the order of magnitude of the displacement at L5 is 1,000 smaller, confirming that it is indeed more resistant to perturbation. In this research, we mainly conducted 3 slingshot missions, and we changed 4 parameters
to accomplish the simulation. As for the initial results, as we can see from the figure, mission 1 and mission 3 are extremely alike. Thus, we analyzed the initial parameter settings in simulation and found that the only difference between mission 1 and mission 3 is the amount of mass. Therefore, we conclude that the mass has a little to do with the slingshot tragedy. Next, we analyze the reverse thrust velocity. Since we slingshot from Earth to L5 point, then there must be a arrival velocity occurs. Therefore, we have to calculate the reverse velocity in order to make the particle stop at L5 point. So we calculated the possible fuel requirements with rocket equation, and the parameters of propulsion system is on the slideshow. Lastly, we get three missions thrust velocity. As you can see from the left and the right graph, they are the slingshot from Earth to L5 point, which are generally the same in outline despite in different masses. For these two cases, there is a tendency for the velocity to increase from the initial velocity and then drop sharply. However, in the middle one, it's the slingshot from Earth to the Moon, and above trend was not observed for this case. Next, the concept of improved Hyperion. It is a new concept that we decided to apply tether extended from the conventional Hyperion to be used in construction of the space elevator. And after the construction, the space elevator can be used as a means of transportation. Thus, we decided to apply a secondary reaction setter, which was conducted by Dr. Paul. Also, the most significant challenge in constructing the Hyperion may be the foundation of the habitat. Therefore, we decided to make a flow work of construction applying space elevator like the figure on the right. As you can see, the constructing multiple space elevators, which is quite hard, but this can ensure that the clinical portion of the foundation assumes a circular shape from a bird's eye view of the moon. The carbon nanotube setters of these space elevators, renowned for their exceptional strengths, will serve as a structural framework for the base of Hyperion.
Next, we consider energy requirements. As an example of life in space, we examine the ISS. It hosts 6 crew members and has a power generation capacity of 75 to 90 kilowatts during the daytime. If we scale this up, Hyperion would need a power generation capacity of about 100 megawatts. As a power generation method, solar power using multi-junction solar cells can be considered. It can achieve a high power conversion efficiency and has been adopted in many space missions, ensuring its reliability. By using the equation on the slide, we find that an area of about 0.15 square kilometer is necessary. Considering reserve power, industrial usage, and the comfort of residents, an even larger area may be required. Additionally, the heat must be dissipated into space. Since all consumed power is ultimately converted into heat, an amount of heat equivalent to the power demand must be radiated away. Using Stefan Boltzmann's law, we calculate that a radiator area of about 0.3 square kilometer is required to effectively dissipate this heat.
At last, the efficiency and cost of time. The estimated mass of the materials to construct Hyperion is around 20 million tons, so the possible transportation will be space elevator or propulsion machines. However, as you can see from the graph, if you use propulsion machine, it will use a long time to accomplish the mission. However, we only need 256.4 years if we use space elevator. Therefore, space elevator was the most promising means from the perspective of both cost and operation time. In conclusion, we investigated the feasibility and efficiency of space elevator for space habitat construction at L5 point. We provided some concept level proposals as photos, and we also conducted research on physics aspects considerations. Moreover, we newly provided an energy utilization cycle with no previous studies and also compared cost efficiency between means. This is the end of presentation. Thank you for listening.
Thank you for listening.